Okay, so this is done well in notes, but I will. So what I've done is I'm going to unwrap right. I'm just going to unwrap it now. Remember how this streamline. Okay, so I'm trying to just look at the top half and just kind of see how maybe I'm going to cut it off right there, perpendicular to the surface, unwrap it, and just draw this developing situation. So what did we say? We sent from A to C. What happened? I like this image. Right, so this top part is my exterior. So this is the idea that, see how this top vector right here is growing, and it can be either growing or shrinking because it's my external flow. And this is this like viscous layer that now has this super strange thing happening because of the curvature of your surface. Right, so over here, right, remember that it's increasing. So really this rate, so this one should actually really kind of be like this. It's really big right there. But so this is increasing. What does that mean? It means we have a adverse. So, and then these had consequences, right? See how that delta is getting smaller, right? And then the shear stress is even getting right? The shear stress is getting larger. So this slope you can see, right, is like and then at C, when I was at the top of the sphere, I had like a maximum. So that means I had maximum shear stress. This is the fastest it's going. And then we get this issue 8. Now we get to this part where it's decelerating. Decelerating gives us an adverse situation. And then right here, here is this point where it decreased so much now, the shear stress here was 0. So at the point D, you have this sort of flat initial point, right? Also could be thought of, because this coordinate right here is Y. If you evaluate this, you get this 0 slope. These are equivalent conditions. And then past that point, it's just going to keep going because this is still getting larger. So that means I already hit 0. I'm going less than 0. So now I have an opposite direction shear. And now you get this situation where your velocity profile goes back in on itself. And that's the terrible thing, because right here, now you're going to get this. Right, this is this separation point where you hit 0 and it pops, and now you have a curl that happened in you. So now it not only did, right, so this is the inviscid part. This is the viscous part. Now what happened is now the inviscid part out here, and now this even becomes rotational. And you get these spiraling eddies and you have this separation. There's no more structure in that boundary layer left because it hit 0. And can you recover it? That's a cool question. So that's sort of, right, all I did was unwind my surface based on streamlines that I had drawn onto it. And you could see how it happened, right? Is after this point, it pops back and you get these swirly points. And you can see here, when this, right, just like we knew from the Reynolds number relationship, when this is accelerating, right, that means my boundary layer is going to start decreasing. When the free stream velocity is decelerating, that means it's going to start to grow. That had implications on the shear stress at the wall, which has implications on the gradient of the velocity profile at the wall, which gives us a situation where, well, if I keep decreasing and I keep decelerating, I'll get to a 0 point, and then past that point, now I'm going to start going the other way, and now you have this separation point. Dandy. So the better thing that comes out of this is the almighty drag coefficient picture or graph that you get for this form drag. So I'm going to, okay, I'll just draw it next video.